So the classification of matter. What is matter? Matter is anything that occupies space and has mass. So I found this t-shirt. You occupy space, you have mass, you mattered. You are matter. So your textbook, your desk, your chair, your body, everything around us, anything that occupies space and has mass is matter. And so when we're talking about a particular instance of matter, we call it a substance. So substance could be, the soda left in my can, it could be the soap in this container, it could be the trash in the can, it could be anything. Right? But a particular instance of matter is substance. There are lots of different kinds of matter, and so we find it useful to classify things. Humans do this with everything. I have several sons, and most of them were very interested in cars and vehicles when they were young. And so they would quickly learn the difference between a truck and a car and a motorcycle, right? And so we can classify vehicles based on how many wheels they have, based on their size, their shape. You could classify them based on what sort of fuel they run on, what color they are, where they came from. There's all sorts of different ways you could categorize vehicles. So in a similar way, there are different ways we can categorize matter. So we can categorize it according to its state, its physical form, or its composition. What are the basic components that make it up? And both of these classifications can be useful. So the states of matter. The three primary states of matter are solid, liquid, and gas. And we classify matter as one of these based on the properties that it exhibits. This is green, but let's think of this in terms of water, because water is something that we're familiar with in all three of its states. When water is in its solid form, we call it ice. Water in its liquid form, we call water, and then water in its gas form is called steam, humidity, whatever, water vapor. So those three different forms are the same substance, and yet they are very different. And the differences come from how the particles within that matter are interacting with each other. So in a solid, here we have an illustration, the particles are fixed relative to each other, and they're very close to each other. So I think of this, students also have three states, and you are currently in the solid state for students. They're sitting in chairs. Those of you who are standing in the same place. We're not moving relative to each other, and we're all kind of crammed together in this room. That's like a solid. A characteristic of solids is that they retain their shape. You take an ice cube out of the tray and you put it on the counter, and it doesn't change its shape. It doesn't change its volume either, because the particles that compose it are stuck together. They're not going to move relative to each other. When that ice cube melts, now its shape changes. And you take water and pour it from one dish to another, and the shape of the water will change, but its volume stays the same. So for students, the liquid state would be when we're in lab. So during lab, we're up and we're moving around. We're still confined to this room, but we're moving relative to each other. And in a liquid, the particles are still touchingly close, but now they're moving relative to each other. In a gas state, the particles are much farther apart from each other. They're no longer touchingly close. The equivalent for this with students is when class is over and people effuse out the door and you go off and you go your separate ways. The volume of a gas will change depending on the container that it's in, because these particles can be varying distances apart, and it will also take on the shape of its container. Oh, that's right, I can't do that. Great. Okay, so I'm going to go through these real quick because I pretty much already said this. So in solid matter, we've got the particles very close to each other, fixed locations. And those particles are not completely still. They are moving. So if you look around at your fellow students, everyone is at least breathing, right? Nobody's keeled over yet. So everyone is moving at least a little bit. Some people are fidgeting, taking notes, whatever, right? We're all moving a little bit. The particles in a solid are moving. They're vibrating. But they're not moving relative to the other particles. So solids have fixed volumes and rigid shapes. How those solids are arranged, how the particles are arranged, give us two more classifications: a crystalline solid versus an amorphous solid. So in a crystalline solid, we have a regular repeating pattern. So in a diamond, which is a crystalline solid, there is a pattern to how these carbon atoms are arranged. It's not just random. It's a specific pattern. So those of you who are sitting at the benches are in a crystalline structure because there's a pattern. You're sitting in rows. Those of you that are around the edge could be considered amorphous. Amorphous means without shape. There's no long-range order. It's random. Another instance of amorphous humans would be kindergartners seated on the floor for story time. They gather around the teacher, and they're not going to sit in rows, right? They're just going to plop down wherever. No long-range order. They go back to their desks and sit in the chairs. Now they're crystalline. They have order.
Question. Mm-hmm. So amorphous is possibly still moving, but moving slowly, or?
So that's a good question. So all particles are moving. In an amorphous solid, being a solid, they are not moving relative to each other, but they are not arranged in a particular pattern. So it'd be a little bit like maybe taking cooked spaghetti and just plopping it on a plate. It's going to be all jumbled and tangled, and there's no order to it. Okay? Any other questions? So liquid state, the matter, the atoms and molecules are very close together, but now they move relative to each other. They slide around. So liquids have fixed volumes. You can't push the pieces any closer together, but the shape will change because they can move relative to each other. And then in the gas, there's a lot of space between the particles. And a result of this is that gases are compressible. So here we have a liquid, no, I'm sorry, that's a solid. It says so right there. Here we have a solid inside of a piston assembly, and if we push down on this piston, we cannot squish it together any further because those particles are already touchingly close. You could imagine those as marbles or something, and you try to squeeze them closer together, and you can't. It's fixed. If you have a gas, there is a lot of empty space between the particles, and so if you press down on that, thanks, Corinne. That was awesome. That's okay. If we press down on that, we can squish them closer together. And so that's why gases have variable volumes. Okay? So that's classifying according to the state. We can also classify by the composition of the matter. So here we've got a flow chart. Up here we have matter. And then we can ask ourselves, well, is the composition of this matter variable? Could it be different, or is it always the same? So if the composition is variable, then that's a mixture. If the composition is not variable, it's a pure substance, meaning it's always the same. In a pure substance, we can look at, can we separate it into simpler substances? If yes, it's a compound. If no, it's an element. So down here we have illustrations. This is water, and this is helium. Helium, like the helium in the Goodyear blimp, is just individual helium atoms. I think of those as little helium Lego blocks. And you can't break those down into smaller pieces. They are as small as they can be. If we look at the water, though, the water, and this illustration always reminds me of little Mickey Mouse heads, right? So the red is his head and the white is the ears, right? So a water molecule is 3 different atoms or Lego blocks stuck together. Can we take the Lego blocks apart? Yes, we can. When we do that, then we have oxygen and hydrogen, which is different than water. And so water is a compound, not an element. Okay, so in a mixture, there's 2 different kinds of mixtures, heterogeneous and homogeneous. And those prefixes hetero and homo mean different and the same. So a heterogeneous mixture, there are different parts to it. So if we look at wet sand, there's water and there's the sand particles, and the water is mixed in among the sand, but you can imagine, say, a mason jar with some water and a scoop of sand, and you can stir it up and it'll mix up, and then when you stop stirring, the sand will settle to the bottom. And there are 2 distinct parts, right? There's the water and the sand. It's not the same throughout. It's different, and so that's heterogeneous. If we put sugar into a cup of tea, or you could put sugar into water and stir it up, the result is different than with sand. And the sugar becomes mixed with the water. We still have 2 different substances here. We have sugar molecules and we have water molecules, but they are thoroughly mixed together and they don't separate on standing. Right? You put the sugar in the tea and you stir it and it dissolves, and the tea at the top is just as sweet as the tea at the bottom. The composition is variable because you could put 1 teaspoon of sugar in there, or you could put 2 teaspoons or 5 teaspoons, right? And you can have a different amount of sugar relative to the water. In a water molecule, the relative amounts of oxygen and hydrogen atoms is always exactly the same. So I've already said most of this. I'll go through it quickly, but it's nice to have the words up there. So the first division is pure substance versus mixture. A pure substance has only 1 component, and the composition is always the same. In a mixture, you have 2 or more different kinds of particles mixed together, and the composition can vary. Those pure substances we can group into elements versus compounds, and this depends on whether you can take those individual particles and break them into smaller particles, or are they already as simple as they can be. So an element cannot be broken down into simpler substances. It's like an individual Lego block. That's as small as you can get. A compound is 2 or more atoms stuck together. They could be atoms of the same element or of different elements, but it's a small Lego structure that you have made out by sticking pieces together. You can take that structure apart. So a compound can be taken apart and separated into elements. Most of the elements are actually quite reactive and are not found by themselves in nature. Most of them combine with other elements to form compounds. Water is a compound, sugar is a compound. For the mixtures, 2 different types of pieces, variable composition, heterogeneous versus homogeneous. And this has to do with how uniformly they mix. Heterogeneous, we've got the composition is different in one region of the mixture than in another. Example would be salt and sand mixed together, or salt and pepper mixed together. And you look at it and you can see there's the little pepper pieces and here are the salt pieces, right? It does not look like it's one uniform substance. In a homogeneous mixture, it appears to be a single substance, even though it is a mixture. What makes it a mixture rather than a pure substance is that it has a variable composition. But that composition is uniform within the entire sample. Yes?
So the variable composition means that like the atoms aren't connecting to like form something new. It's just like you dissolve the sugar in it.
Right. So let's go back, if I can, to this picture here. So if we look at these helium and pure water, both of these are examples of a pure substance. We see that there is one kind of individual particle, the helium atom. Here, those individual particles are more complicated, but all the particles are the same. They are all water molecules, 1 oxygen, 2 hydrogens. They're all the same. Over here, we have a mixture. There are 2 different kinds of particles. And so we could have more or less of the water compared to the sand. Here we have sugar and water, and we could have more or less. The proportions can be different. It's a mixture because there are 2 different kinds of particles. The difference between the the compound and the helium, let's start that one over again. The difference between the compound and the element is the particles in a compound can be taken apart. Now that might be pretty difficult to do, but it's possible. You can take the water apart into hydrogen and oxygen. Does that help? Anybody else have questions? There are a lot of these things that once you can see it, it's easy and it makes a lot of sense. But if you can't see it, it's just like some weird mystery. It's like those pictures where you have to kind of let your eyes go out of focus before you can see the picture. Once you see it, then you can't really unsee it. But I have a real hard time seeing those things. It just looks like a bunch of dots, and what is there, right? So I want to encourage you, if you're not seeing the picture I'm trying to paint for you, please ask questions, okay? Oh gosh. Okay, so here's a conceptual connection. In these images, a blue circle represents an atom of one kind of element, and a red square represents an atom of another element. Which of these images is a pure substance? So one of these is a pure substance, and the other 2 are mixtures. So in panel A here, we have a blue circle and a red square, and they're connected with this little line, right? And if we look at all the individual pieces here, they all are the same, a blue circle and a red square. Over here, we have individual blue circles and red squares, and they're all jumbled together. Over here, we also have individual circles and squares, but now they're kind of clumped up, right? So which of these represents a pure substance? It's A. Because all the particles are the same. They're all composed of the same things, a blue circle and a red square. Now, could we break that into simpler things? Yes, we could. So this is a pure substance, but it would be classified as a compound rather than an element. Panel B and C then are mixtures. Which of these is homogeneous? B. B is homogeneous, or relatively so, and C is definitely heterogeneous, because this composition up here is all blue circles, and down here it's all red squares. And here it's much more uniformly mixed together. Any questions? So mixtures can be separated. Because if you work hard enough, look hard enough, you can find different properties from that the different components have different properties. Those might be physical or chemical properties, and you can make use of those differences to separate the components. So thinking back to our example of sand and water, you got a mason jar with some water in it, and you've dumped some sand in there, you stirred it up, and now you let it sit, and the sand settles to the bottom. We can separate the water from the sand by carefully pouring the water out of the jar and leaving the sand behind. That's a chemical technique called decanting. Just pouring it carefully off the top, and we'll be doing that in lab one day. Now, does that get all the water out of the sand? No, but it does get all the sand out of the water, right? And so that's a separation. If we have a homogeneous mixture of liquids, say alcohol and water, how do we separate those? We can't just pour one off because they're thoroughly mixed together. But we can make use of the different boiling points of water and alcohol and do a distillation. So in a distillation, we have our mixture here and we're going to heat it. The alcohol will evaporate, it will boil at a much lower temperature than the water. And so as this heats up, the alcohol will go into the gas state. It's more volatile. And we put a stopper here because we want to collect it. We don't want to just let it get away. And so we're going to direct it through this tube here. It's called a condenser. It's a double-walled tube. It's got an outer jacket that we can run cold water through. So you take that gas and you cool it down, and it condenses back into a liquid. And then it's going to run down, and we're going to collect it in this flask here. So as this process continues, the alcohol is going to be removed from the mixture, and it's going to end up over here, and what's going to remain behind is an increasingly high concentration of water. And eventually, you'll get them separated. Filtration is a method we use a lot in everyday life. Anybody make coffee this morning? You did a filtration. If you've ever cooked spaghetti or any sort of pasta, you've done a filtration. Because what do you do with the pasta? Do you serve it in the pot of boiling water? No. You pour it into a colander, right? Colander's a big bowl with holes in it. You have two components there in your heterogeneous mixture. You have the pasta, which is solid, and the hot water, which is a liquid. The water will go through the little holes. The pasta does not. Ta-da, you've separated them. For something like coffee or something that, a precipitate that we run into in chemistry lab, we're more likely to use a funnel with a piece of filter paper. So paper, like your coffee filter, is porous and will allow liquid to go through, but will catch the solid. It wouldn't work to make coffee in a colander because the holes are too big and all the grounds would just go through and it wouldn't accomplish anything. So here we're pouring this liquid containing a solid into the funnel, and the filter paper is retaining the solid and the liquid is allowed to go through. And so we separate the mixture based on differences in physical state.